Assalamu alaikum, dear student. This is lecture number 1 of week number 10, and probably this is our last week for uploading the lectures. So let's see what are the topics we are going to cover in the today's lecture. And still we are continuing the chapter number 8, the viscous flow in pipe. So these are the learning objectives that we have set up at the beginning of the chapter. So far we have already derived the equation for the pressure loss in the straight pipe, and in this so up to here we have covered, and also we have covered a part of this learning objective. So let's see the to achieve this learning objective, what are the topics we are going to cover today. So pressure drop and head loss for the inclined pipe we are going to cover today, and pressure drop and head loss in the straight pipe we have already derived in the previous lecture, and also the fully developed laminar flow summary, because these calculations we are doing so far only for the laminar flow. Okay, so what we have done in the previous lecture so far, so we will see the summary, and also the laminar flow in non-circular pipe. Okay, how do we deal with the pressure drop and head loss in non-circular pipe, we will see, and type of fluid flow problems, and we will see the fluid flow problem for these particular case for the laminar flow, for the fully developed laminar flow in the pipe. Okay, and the practice problem we will perform. We will see the difference between the turbulent velocity profile and the laminar velocity profile, and also we will discuss the Moody chart and the importance of Moody chart and the requirement of the Moody chart. So let's start the topic today. So previously we have discussed this part, the pressure drop and head loss in a straight pipe, and this is the Bernoulli equation we applied at 2 point of the streamline. Okay, so here at the point 1 we have some equipment, and we have a pressure drop in the form of head loss. Okay, because all the equation has been written in the form of head loss, and this is the whole equation is written in the form of the pressure. Okay, if you need the energy loss in the form of pressure drop or in the form of head loss, we can calculate by using these formulas. Okay, and here also if you have add up any equipment to add the energy in the fluid, so we can put in the at section 1, and if you are consuming energy by some other equipment, so we have the case of turbine, and here is the case of pump. Okay, so let's go and see the pressure drop and head loss for the inclined pipe. So basically we have discussed in detail how to drive equation for the pressure drop and head loss for a straight pipe. For the inclined pipe it's not much difference. Okay, because the pressure drop and head loss in a straight pipe is a special case of the pressure drop and head loss in an inclined pipe, because if theta is 0, so it will be a case of a straight pipe. If the pipe is making some angle with the horizontal axis or the vertical axis, so definitely there is a difference in derivation. So the same procedure we will follow. So it is so I advise you to perform this derivation by yourself. Okay, the guideline is given, but see how we have performed that. Okay, the same procedure we have followed to drive the equation for the straight pipe. Okay, so but so what are the assumptions we have made at the beginning of derivation of this equation, so that you have to see. and this is the final equation we have received. So this is indicating that if the pipe is even inclined, okay, so the fully developed laminar flow has a velocity profile which is a parabolic shape. Okay, this is a second degree equation, or it's showing a parabolic shape. Okay, so this is the equation indicating that. And here this is by using the Poiseuille's law. So this is the volume flow rate that we have derived for the inclined pipe. Okay, when you will continue derivation, you will get up. So you see, here are the cases when the theta is greater than or less than 0. So this equation will be applicable. Even if theta is equals to 0, this equation will be applicable, and sine 0 is equals to 0. So this will become the same equation we have derived for the straight pipe. Okay, and here is the summary for the fully developed laminar flow. Okay, in the pipe, if the flow after entering region, if the velocity profile achieve a fully developed laminar flow, so these equations are applicable. Okay, so here these equations are applicable only for the fully developed laminar flow, and based on that we will also perform some practice problem. So here is the here you can see this is the velocity profile that we have derived for the straight pipe as well as for the inclined pipe, and this is the average velocity. Okay, this is the average velocity, indicating this is VC. VC is basically the maximum velocity. Okay, VC is indicating a maximum velocity, and V is equals to basically the average velocity. So average velocity in a fully developed laminar flow is half of the maximum velocity, and this is the value of the maximum velocity. If you divide by 2, it will become VC by 2. Okay, and this is the equation we derive by using the Poiseuille's law. So the volume flow rate is equal to these values. Okay, for the this is for the straight pipe, and this is for the inclined pipe. Okay, this is for the inclined pipe, and this is for the straight pipe. This is the head loss. Okay, this is the head loss. Head loss equation is same for the inclined pipe or for the straight pipe. Okay, only the difference is delta P. So if you are calculating delta P, so all equation is going to be same. So here F is basically a friction factor. Okay, for the laminar flow, F is equals to 64 by Reynolds number. Okay, this we have derived from here. Okay, we know the F is equals to 64 by Reynolds number, so we have replaced, okay, here the F by using here you can see delta P is equals to this and delta P. Then finally we have convert the Reynolds number, okay, into F. So F is equals to 64 by RE, that we have previously discussed in detail. This is just a summary. Okay, so let's see the laminar flow in non-circular pipe. So if the flow, because these equations are derived for the circular pipe, okay, but if the fluid is flowing from a non-circular pipe, then how we can calculate the pressure drop? Okay, so this is, you can see here the ratio A by B is given. Okay, and friction factor F for the fully developed laminar flow is 64 by RE for the circular pipe. For the non-circular pipe, you know, we can convert the diameter. The only difference is the diameter and the dimension of the non-circular duct or pipe. So whatever is the dimension of the non-circular pipe, we have a procedure to convert the non-circular dimension into a hydraulic diameter. So this is the way to convert the non-circular dimension into hydraulic diameter, that we have also previously discussed in detail in the Reynolds number topic. Okay, so here you see, you can see if if the ratio of larger side to the smaller side is this, the Reynolds number for that particular cross section will be this. Or you can also directly convert by using this formula. Okay, so here are the equation you can see for the elliptical shape, here for the triangular shape cross section pipe or duct, whatever we are using. So this is how we convert the non-circular duct or pipe into a hydraulic diameter. Okay, and this will help to solve the problem for a non-circular pipe. So let's see the type of problem normally we come across in such fully developed laminar flow. If the fluid is passing through a pipe and the flow is fully developed laminar, so what a laminar or turbulent, so whatever is the fully developed laminar or turbulent flow. Okay, so these are the type of problem normally we face in the practical life. So sometime we determine delta P or head loss when these items are given. Okay, and this also can be unknown. We can determine mass flow rate is also unknown, but some other information, velocity is given, area is given, we can calculate. So here we can also determine volume flow rate when these values are given. Here we can determine volume flow rate when these items are given. Okay, so these are the type of problems we basically face, and we can find out if the informations are given. Okay, so the type 2 and type 3 are common engineering design problems. Selection of pipe diameter to minimize construction and pumping cost. Okay, so normally either we determine pressure drop in the pipe, or determine if the pressure drop is given, diameter we determine. If the pressure drop and diameter and lengths are given, we determine the volume flow rate. Okay, so these are the types of problem we face in our practical life. So however, iterative approach required since both V and D are in the Reynolds number. Okay, so let's see some of the practice problem for the fully developed laminar flow. So here consider a flow rate in a horizontal inclined pipe. If first we are dealing with the horizontal and inclined pipes. In both the cases we are going to deal at the same time, if the pipe is horizontal and pipe inclined. So how it is? Oil at 20 degrees centigrade, the density of the oil and viscosity of the oil is given. Okay, if it is not given, so if the type of the oil or the type of the fluid is given, we can determine these properties by using the properties table. Okay, just keep in mind. Okay, if the type of the fluid is given, the temperatures are given. Okay, so we can determine the fluid properties by using the table if it is not given in the exam. Okay, or in the problem, so we can directly consult with the properties table. Is flowing steadily through a 5 centimeter diameter. You fully understand the meaning of steadily or steady state. Okay, when things do not change with respect to time. Okay, so is flowing steadily through a 5 centimeter diameter. Okay, diameter of the pipe is 5 centimeter and the length of the pipe is 40 centimeter. The pressure at the pipe inlet and outlet are measured to be 75 and 97 kilopascal. The pressure at the inlet and outlet is given. Okay, that means delta P is known. Okay, so okay, respectively determine the flow rate of oil through the pipe assuming the pipe is horizontal, inclined, okay, and 15 degree downward. Also verify that the flow through the pipe is laminar. Okay, so we also have to determine the flow is laminar. So here are the diagram. You see, if the first case, when the pipe is horizontal, when the pipe is 15 degree upward, when the pipe is 15 degree downward. So this is the case. So first of all, what we have to do, The pressure reading at the inlet and outlet of a pipe are given. The flow rates are to be determined for 3 different orientation, and the flow is to be shown to be laminar. So these are our objectives that we have to perform. So here we are going to make some assumptions. The flow is steady and incompressible. The fluid must, we have to consider it is incompressible. If it is not incompressible, then the dealing with the fluid is totally going to be different, and the equation we have drive is going to be different. Okay, so the entrance effects are negligible. We know the entrance effect at the entrance of the pipe. The flow is neither laminar neither turbulent. Okay, the flow achieve its laminar or turbulent shape after the entrance region or after the entrance length. Okay, where the fully developed laminar or turbulent flow is achieved. Okay, so where dx by du by dx is constant. Okay, I mean the velocity along the axis of the pipe is constant. So thus the flow is fully developed. The pipe, okay, so this we are also assuming that the flow is fully developed. Okay, because the equation we have derived so far, that is for the fully developed laminar flow. Okay, even we haven't developed an equation for the fully developed turbulent flow. Okay, the pipe involves no components such as bend, valve and connectors. So these equations are applicable only for the, and so far what we have studied is for the straight pipes. Okay, there is no bends and valves are considered. Okay, the piping section involves no work devices such as pumps or turbine, and also there is no pump and turbine we are considering. Okay, so let's see the next. So here the properties of the fluids are given that we have highlighted here. Okay, the density and viscosity of the this is the dynamic viscosity, or the viscosity or density is given. So the flow rate for all 3 cases can be determined by using the below equation. So this is the equation we have derived for the inclined pipe. Okay, so this equation is valid for all 3 type of orientation. Okay, so here you see what are the things are unknown, because you see the length is given, the viscosity is known, theta is known. Okay, the length is given, specific weight is given, delta p is given, and diameter is given. All the informations are given. Okay, but we have to make sure that the flow is laminar. Okay, that we have to also make sure, also verify that the flow through the pipe is laminar. So here you see the pressure drop across the pipe and the pipe cross sections are, okay, so this is the pressure drop delta P we have calculated at the inlet and exit. Okay, so here you see the pressure is dropped due to the viscous effect from 745 kilopascal to the 90 kilopascal. It's reduced, okay, because of the friction losses in the pipe. Okay, friction losses basically due to the surface roughness, in the pipe. Okay, and this is the cross section area. Okay, this is the cross section area of the pipe. So now here, okay, so here theta is given, the angle is the angle the pipe makes with the horizontal axis. Okay, so this is the horizontal axis and it's making an angle. So let's solve the problem one by one. In the first case, if the pipe is horizontal, if theta is equals to 0, when theta is equals to 0, then sine 0 is equals to 0, so it will become pi delta p d4 128 mu l. So here it is given. Okay, here it is given the case for the horizontal case, this is the volume flow rate we achieved. So make sure that all the units are properly converted. Okay, here if you see, if the pressure is given in bar, so the bar must be converted in kilopascal. If the pressure is given, if the force is given in dyne, it must be converted. If you are using a SI system, the all unit must be properly converted. Okay, if any dimension is given in inches, feet or centimeter, it has to be converted into the SI system. Okay, for the uphill condition, you can see for the uphill condition, the flow with the incline theta is equals to plus 15 degree. So sine 15 degree, we resolve it, and finally we got the volume flow rate for the uphill condition. And same when theta is equals to minus 15 degree. Okay, so just calculate the same way that we have calculated, because all the parameters are known. So we have converted into the volume flow rate, so which is 0.00354. So here it is, you can see in the straight pipe, the volume flow rate, the quantity is this, but in the downhill condition, the volume flow rate is maximum. You can see the volume flow rate is maximum. So volume flow rate is basically what? Because the diameter is constant throughout the pipe, so only thing is varying in all three cases are the velocity. Okay, here is the volume flow rate is this, because diameter is constant. In all three cases, the diameter is constant, so only thing which is varying, that is the velocity. So velocity in that case will be maximum, because the volume flow rate in that particular case is maximum. Okay, so now we are going to verify that the flow is laminar or not. So to verify the flow is laminar or not, we have a parameter that is called a Reynolds number. Basically, Reynolds number determine whether the flow in pipe is turbulent or laminar. So we are considering the case of a maximum velocity, because where the flow rate is maximum, so we are considering in that case velocity is maximum, because the Reynolds number is directly proportional to the velocity. You see, all those parameters are constant, only the parameter which is not varying, that is velocity. Which is varying, that is velocity. Rest of the parameters are the fluid properties or the geometrical properties, okay, that are not varying. So the Reynolds number here is depending on the velocity. So if the velocity is higher, okay, the flow may be laminar or turbulent. But if the flow is laminar in higher velocity, okay, so definitely the flow will be laminar in the lower velocity. So we are going to deal with the higher case only. Okay, so here we calculated the average velocity. Okay, volume flow rate divided by the cross section area, so we got 1.8 meter per second, and we got the Reynolds number is 100 because it's a dimensionless number, so there is no unit. So for the circular pipe, okay, for the straight pipe, okay, or for the circular pipe, the Reynolds number, if the Reynolds number is less than 2300, okay, the Reynolds number is less than 2300, that means the flow is laminar. So our Reynolds number is 100, so that means our flow is laminar. So this is the discussion. For the rest of the discussion, you can read yourself to understand what I have explained already. So now the case number 2, water at 40 degree Fahrenheit is given, and the fluid properties we have already considered. So first case we have discussed in SI system, now this is in FPS system. Okay, so here, if as I told you earlier, if the properties are not given, you can calculate these properties from the tables, and the tables are given both in SI system and FPS system. Okay, okay, for the water and other fluid as well, for a different temperature. Okay, or if not, then you have to compile your own property tables. Okay, okay, so here the flowing through a 0.1 inch diameter, okay, or 30 feet long horizontal pipe steadily at an average velocity of 3 feet per second. Determine the head loss. In the first case we just derived the volume flow rate. Now here we are going to determine the head loss. Okay, the pressure drop and the pumping power requirement to overcome this pressure drop. You see, if higher the pressure drop, the more the pumping power will be required. So as an engineer, our objective to reduce the pressure drop as much as possible whenever we design the piping network. Okay. So here what we have to do, we have to determine the head loss, the pressure drop, okay, and the pumping power requirement. Okay, these three things we have to determine. So to determine this, so let's see, this is the pipe is given, the diameter is given, okay, and the velocity is given, and the length of the pipe is given. Okay. So the average flow velocity in a pipe is given, the head loss, the pressure drop, and the pumping power are to be determined. Okay, so here the assumptions we are going to make: the flow is steadily and incompressible. It is very important assumption. The entrance effects are negligible, and thus the flow is fully developed. Okay, so we are considering the flow is fully developed. We are not saying it is laminar or turbulent, so that we will decide. Okay, but we are saying we are considering the flow is fully developed, because if the flow is fully not fully developed, then we cannot apply any equation that we have derived previously. Okay, so the pipe involve no components such as bands, valves, and connectors. So we are just considering the straight pipes. Okay, and here are the properties which is given. And now analysis. First we need to determine the flow regime, the Reynolds number. So flow regime means we have to determine whether flow is laminar or turbulent. Okay, so to determine the flow is laminar or turbulent, first step we find out the Reynolds number. So this is the equation of Reynolds number, and we calculated, we put all the, but make sure all the units are properly converted into same system of units. If it is not, so the answer will be wrong and all the efforts you have done will be wrong. Okay, because this is the basic thing that we have to understand. Okay, so the Reynolds number is 1803, which is less than 2300. Okay, so that means the flow is fully developed laminar flow. Okay, so now noting that the pipe is horizontal and its diameter is constant. Okay, the pressure drop in the pipe is due to entirely to the friction loss, and it is equivalent to the pressure loss. Okay, so the pressure drop is basically due to the surface roughness or the friction losses. Okay, so this is basically the friction factor. Okay, to find out the head loss, this is the formula we have. Okay, in the formula we have velocity is known, length is known, diameter is known. Only thing which is unknown, that is friction factor. And for the laminar flow, that we have already confirmed the flow is laminar. If the flow is laminar, the friction factor can be determined by using this formula 64 by Re. This is for the friction factor formula for the laminar flow. So Reynolds number we have already calculated, it is 0.0355. Okay, so the head loss we calculated is 14.9 feet. Okay, so now we converted this head loss into pressure, into pressure loss. Okay, so we converted it. This is the formula for the pressure drop. Okay, so same we have converted, and finally we have to calculate the pumping power. And the pumping power we can calculate, the volume flow rate and the pumping power requirements are, okay, so volume flow rate we can calculate, Q is equals to VA, area of cross section, into average velocities, that we have calculated. And pumping power, we know that if we multiply with the pressure drop to the volume flow rate, we can achieve the watts. So you can convert, you can multiply this, and you can convert its unit also, because the unit of the pressure difference is Newton per meter square, and here the volume flow rate is what, meter cube per second. So if you convert them together, you will get a watts. Okay, so if you multiply the volume flow rate with the pressure drop, so you will get the pumping power required. Okay, to overcome this much pressure drop for this much flow, so this much power of the pump you will require. Okay, So here, therefore, the power input in the amount of 0.3 watts is needed to overcome the friction losses in the flow due to the viscosity, due to the viscous effect, definitely. Okay, so we have seen this, that previously, if there is no if the flow is inviscid, there is no friction loss, the energy at point 1 is equal to the energy at point 2. Okay, there is no pressure drop we have observed. Okay, so this is basically the two practice problem for the fully developed laminar flow. We will see in the next lecture, if the flow is fully turbulent, then how do we determine the pressure drop and other parameters. We will see in the next lecture. Okay.